completed by a third nail, C, which was laid loosely across the other two. Any vibrations in the air in the vicinity caused variations in the intimacy of contact between the nails, and corresponding variations in the resistance of the circuit. This was a very inefficient form of transmitter, but it demonstrated the principle of loose contact very cleverly. It was found that carbon was, for various reasons, by far the most desirable substance for electrodes in the loose contact transmitter, and nothing has ever been found to approach it in efficiency and desirability. Another form of transmitter devised by Hughes and called by him the microphone is shown in Figure 39. This consists of a small pencil of gas carbon, A, pointed at each end, and two blocks, B and B, of carbon fastened to a diaphragm or sounding board, C. These blocks are hollowed out in such a manner as to loosely hold between them the pencil, A. The blocks, B and B, form the terminals of the circuit. This instrument, though crude in form, is of marvelous delicacy and is well termed microphone. The slightest noises in the vicinity, and even those incapable of being heard by the ear alone, produce surprising effects in the receiving instrument. This particular form of instrument is in fact too delicate for ordinary use, as any jar or loud noise will cause the electrodes to break contact and produce deafening noises in the receiver. Nearly all carbon transmitters of today are of the loose contact type, this having entirely superseded the first form devised by Edison, which was then supposed to depend upon the actual resistance of a carbon block being changed under varying pressure. In speaking of Professor Hughes' work on loose contacts and the microphone, the Telephone Journal and Electrical Review, an English paper, says in its issue of July 1, 1878, quote, "The microphone is a striking illustration of the truth that in science any phenomenon whatever may be turned to account. The trouble of one generation of scientists may be turned to the honor and service of the next. Electricians have long had sore reasons for regarding a bad contact as an unmitigated nuisance, the instrument of the evil one, with no conceivable good in it and no conceivable purpose except to annoy and tempt them into wickedness, and an expression of hearty but ignominious emotion. Professor Hughes, however, has with a wizard's power transformed this electrician's bane into a professional glory and a public boon. Verily, there is a soul of virtue in things evil." Unquote. Professor Hughes, in an article in Nature, June 27, 1878, thus describes the condition necessary for microphonic action. Quote, "If the pressure on the materials is not sufficient, we shall have a constant succession of interruptions of contact, and the galvanometer needle will indicate the fact. If the pressure on the materials is gradually increased, the tones will be loud but wanting in distinctness, the galvanometer indicating interruptions. As the pressure is still increased, the tone becomes clearer, and the galvanometer will be stationary when a maximum of loudness and clearness is attained. If the pressure be further increased, the sounds become weaker, though very clear, and as the pressure is still further augmented, the sounds die out, as if the speaker was talking and walking away at the same time, until a point is arrived at where there is complete silence." Unquote. Only one radical improvement now remains to be recorded. In 1881, Henry Hunnings devised a transmitter wherein the variable resistance medium consisted of a mass of finely divided carbon granules held between two conducting plates. His transmitter is shown in Figure 40. Between the metal diaphragm A and a parallel conducting plate B, both of which are securely mounted in a case formed by the block D and a mouthpiece F, is a chamber filled with the fine granules of carbon, C. The diaphragm A and the plate B form the terminals of the transmitter, and the current from the battery must therefore flow through the mass of granular carbon, C. When the diaphragm is caused to vibrate by sound waves, it is brought into a more or less intimate contact with the carbon granules and causes a varying pressure between them. The resistance offered by them to the current is thus varied, and the desired undulations in the current produced. This transmitter, instead of having one or a few points of variable contact, is seen to have a multitude of them. It can carry a larger current without heating, and at the same time produce greater changes in its resistance than the forms previously devised, and no ordinary sound can cause a total break between the electrodes. These and other advantages have caused this type in one form or another to largely displace all others. At first, the practice was to put the transmitter, together with the receiver and battery, directly in circuit with the line wire. With this arrangement, the changes produced in the resistance by the transmitter were small in comparison with the total resistance of the circuit, especially in the case of a long line, and the changes in current were therefore small. Edison remedied this difficulty by using an induction coil in connection with the transmitter. The induction coil used then and now is made as follows. Around a core formed of a bundle of soft iron wires is wound a few turns of comparatively heavy insulated copper wire. Outside of this, and entirely separated from it, is wound another coil consisting of a great number of turns of fine wire, also of copper and insulated. The transmitter, together with the battery, is placed in a closed circuit with the coarse winding of a few turns, while the fine winding of many turns is included directly in circuit with the line wire and the receiving instrument. The coarse winding is usually termed the primary winding, because it is associated with the primary source of current, the battery, while the fine winding is usually termed the secondary winding because the currents flowing in it at the transmitting station are secondary or induced currents. In coils of this kind, the coarse winding is almost invariably termed the primary for the above reason, although many conditions exist in electrical work and in telephone work where the high resistance winding is in reality the primary coil. The circuit arrangement spoken of is shown in Figure 41, in which T is a transmitter, B a battery, P and S primary and secondary windings respectively of an induction coil, L and L the line wires, and R the receiving instrument. It is well to state here that the usual way of indicating the primary and secondary of an induction coil in diagraphic representation of electrical circuits is by an arrangement of two adjacent zigzag lines, as shown in Figure 41. A current flowing in the primary winding of the induction coil produces a field of force in the surrounding space, and any changes caused by the transmitter in the strength of the current produce changes in the intensity of this field. As the secondary winding lies in this field, these changes will, by the laws of Faraday and Henry, cause currents to flow in the secondary winding and through the line wire to the receiving instrument. In good induction coils, the electromotive forces up in the secondary coil bear nearly the same ratio to the changes in electromotive force in the primary coil, as the number of turns in the secondary bears to the number of turns in the primary. The use of the induction coil with the transmitter accomplishes two very important results. First, it enables the transmitter to operate in a circuit of very low resistance, so that the changes in the resistance produced by the transmitter bear a very large ratio to the total resistance of the circuit. This advantage is well illustrated by contrasting the two following cases. Suppose a transmitter capable of producing a change of resistance of 1 ohm be placed directly in a line circuit whose total resistance is 1,000 ohms. A change in the resistance of the transmitter of 1 ohm will then change the total resistance of the circuit 1/1000th of its value, and the resulting change in the current flowing will be but 1 1/1000th of its value. On the other hand, suppose the same transmitter to be placed in a local circuit as above described, the total resistance of which circuit is 5 ohms. The change of 1 ohm in the transmitter will now produce a change of resistance of 1/5 of the total resistance of the circuit, and cause a change of 1/5 of the total current flowing. It is thus seen that fluctuations in the current can be produced by a transmitter with the aid of an induction coil, which are many times greater than those produced by the same transmitter without the coil. The second advantage is that by virtue of the small number of turns in the primary winding and the large number in the secondary winding of the induction coil, the currents generated in the secondary are of a very high voltage as compared with those in the primary, thus enabling transmission to be effected over much greater length of line, and over vastly higher resistances than would be possible if the transmitter were forced to vary the current flowing through the entire length of the line. Neither the telephone receiver nor the transmitter have undergone any radical changes since their early days. Various minor details have received the attention of engineers and inventors, but the magnetotelephone is still the receiver, and the variable resistances of the carbon contacts the means of transmission. The principal developments have been in the means of intercommunication. The growth of the telephone industry has been very rapid, and from being a luxury, the telephone has become a business necessity. The tendency has been toward the simplification of the subscriber's station and the improvement of the central office. The battery current for talking is now supplied in concentrated communities from the central station. Considerable trouble formerly was experienced through the deterioration of the battery at the subscriber's station. The telegraph phone, or the telephonograph, is an instrument which records magnetically sounds produced at a distance. It was originated by Mr. Paulsen, a Danish inventor. Figure 43 shows the essential parts. Either a steel band is used or a long steel wire, rolled from one drum to the other, under the recording magnet which receives the talking currents and engraves them magnetically upon the steel wire. To reproduce the message, it is only necessary to pass the steel wire under a reproducing magnet connected to a telephone receiver, the reproduction being very perfect. The message may be erased from the wire by means of the obliterating magnet supplied with an alternating current. End of section 27.
Section 28 of The Science History of the Universe, Volume 3. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Avai in August 2016. The Science History of the Universe, Volume 3, edited by Francis Rolt Wheeler. Electricity. Chapter 9. Electric Railways. Although the earliest recorded experiments date back 3/4 of a century, the electric railway is essentially of modern development, for it achieved the recognized position less than 20 years ago, long after the telephone, the arc and incandescent lamp, and the stationary electric motor had been thoroughly established. This is but natural, for it is the logical outcome of the establishment of certain cardinal principles and practices in the kindred arts. The first roads to carry passengers commercially were built in Europe, but the first railway experiments and the modern commercial impetus, as well as most of the essential and distinctive features of the art as it stands today, an example of almost unprecedented industrial development, are distinctively American, as Frank J. Sprague pointed out in his paper before the Electrical Congress of 1904, from which much of the following matter is taken. Brandon, Vermont, birthplace, and Thomas Davenport, blacksmith, father, are the names first on the genealogical tree of the electric railway in the year 1834. A toy motor mounted on wheels, propelled on a few feet of circular railway by a primary battery, exhibited a year later at Springfield and again at Boston, is the infant's photograph. This was only 3 years after Henry's invention of the motor, following Faraday's discovery 10 years earlier that electricity could be used to produce continuous motion. The records of Davenport's career, unearthed by the late Franklin Leonard Pope, show this early inventor a man of genius, deserving a high place in the niche of fame, for in a period of 6 years he built more than 100 operative electric motors of various designs, many of which were put into actual service, an achievement, taking into account the times, well nigh incredible. For nearly 20 years, various inventors, handicapped with the limitations of the primary battery and in utter ignorance of the principles of modern dynamo and motor construction, labored with small result. The invention by Paginotti in 1861 of the continuous current dynamo may properly be said to date all modern electric machines. These were developed in their earliest forms by Graham and Siemens, Wheatstone and Varley, Farmer and Rowland, Hefner-Alteneck and others, and brought into existence the elements essential to any possible commercial success. Yet, notwithstanding that the principle of the reversibility of the dynamo electric machine and the transmission of energy to a distance by the use of two similar machines, said to have been discovered and described by Paginotti in 1867, the same year in which Professor Farmer described the principle of the modern dynamo in a letter to Henry Wilde, and demonstrated independently at the Vienna Exposition by Fontaine and Gramme in 1873, many years more passed before the importance and availability of this principle were generally recognized. From 1850 to 1875 is a long period relatively, and yet there seemed to have been practically an entire cessation of experimental electric railway work until in the latter year George F. Green, a poor mechanic of Kalamazoo, Michigan, built a small model motor which was supplied from a battery through an overhead line, with track return, and 3 years later he constructed another model on a larger scale. Green seemed to have realized that a dynamo was essential to success, but he did not know how to make one and did not have the means to buy it. Shortly afterward, in 1879, at the Berlin Exposition, Messrs. Siemens and Halske constructed a short line about 1/3 of a mile in length, which was the beginning of much active work by this firm. The dynamo and motor were of the now well-known Siemens type, and the current was supplied through a central rail, with the running rails as a return, to a small locomotive on which the motor was carried longitudinally, motion being transmitted through spur and beveled gears to a central shaft from which connection was made to the wheels. The locomotive drew 3 small cars having a capacity of about 20 people and attained the speed of about 8 miles an hour. Perhaps more than to any other, the credit for the first serious proposal in the United States should be awarded to Field. Curiously enough, patent papers were filed by Field, Siemens, and Edison, all within 3 months of each other, in the spring and summer of 1880. Priority of invention was finally awarded to Field, he having filed a caveat a year before. He had been actively interested in electric telegraphs, and in an account of his work published some 20 years ago, it is stated that he early constructed 2 electric motors and had in mind the operation of streetcars in San Francisco, but had not been able to do anything in the matter because of a realization that a dynamo must be used instead of a battery. In 1877, while in Europe, he saw some Gramme machines, and on his return 2 of them were ordered, but not delivered. Later, a dynamo was ordered from Siemens Brothers in London, which was lost, and this was replaced by another which arrived in the fall of 1878. Meanwhile, 2-gram machines were placed at his disposal, and shortly afterward an electric elevator was operated. In February 1879, he made plans for an electric railway, the current to be delivered from a stationary source of power through a wire enclosed in a conduit, with rail return, and in 1880 to 81 he constructed and put in operation an experimental electric locomotive in Stockbridge, Massachusetts. Pending the settlement of patent interferences between Edison and Field, the Siemens application being late was rejected, the two interests were combined in a corporation known as the Electric Railway Company of the United States, and the first work of the company was the operation of an electric locomotive at the Chicago Railway Exposition in 1883. The locomotive, called the Judge, after the late Chief Justice Field, ran around the gallery of the main exposition building on a track of about 1/3 of a mile in length. The motor used was a Western dynamo mounted on the car and connected by beveled gear to a shaft from which power was transmitted by belts to one of the wheels. The current was taken from a center rail with track return. A lever operated clutches on the driving shaft, and the speed was varied by resistance. The reversing mechanism consisted of two movable brush holders geared to a disc operated by a lever, each arm carrying a pair of brushes, one of which only could be thrown into circuit at a time to give the proper direction of movement. Meanwhile, several other inventors were getting actively into the field of transmission of power and electric railways. In the summer of 1882, Dr. Joseph R. Finney operated in Allegheny, Pennsylvania, a car for which current was supplied through an overhead wire on which traveled a small trolley connected to the car with a flexible cable. And about the same time in England, Dr. Fleming Jenkin, following a paper by Messrs. Ayrton and Perry before the Royal Institution on an automatic railway, proposed a scheme of telpharage which was developed by those gentlemen. In the early part of the same year, the writer Mr. Sprague, then a midshipman in the United States Navy, who had in 1879 and 1880 begun the designing of motors, was ordered on duty at the Crystal Palace Electric Exhibition, then being held at Sydenham, England. While in London, he became impressed with a belief in the possibility of operating the underground railway electrically. He first considered the use of main and working conductors, the latter being carried between the tracks, with rail return, but noting the complication of switches on certain sections of the road, conceived the idea of a car moving between two planes, traveling on one and making upper pressure contact with the other, those planes being the terminals of a constant potential system. For practical application, the lower of the two planes was to be replaced by the running track and all switches and sidings, and the upper plane by rigid conductors supported by the roof of the tunnel and following the center lines of all tracks and switches, contact to be made therewith by a self-adjusting device carried on the car roof over the center of the truck and pressed upwards by the springs. In 1882, he applied for a patent on the first idea, which was but a variation from that shown in other patents, but the second lay dormant for nearly 3 years because of central station work and the development of the application of stationary motors. Meanwhile, in the United States, Charles J. Van de Poel, a Belgian by birth and a sculptor by original trade, and an indefatigable worker, had become interested in electric manufacture and soon energetically attacked the railway problem. His first railway was a small experimental line constructed in Chicago in the winter of 1882 to 83, the current supplied from an overhead wire. In the fall of 1883, a car was also run at the Industrial Exposition at Chicago. A year later, a train pulled by a locomotive and taking current from an underground conduit was successfully operated at the Toronto Exhibition to carry passengers from the streetcar system, And again in the year following, Van der Poel operated another train at the same place, using on this occasion an overhead wire and a weighted arm pressing a contact up against it. Experiments were also carried on by him on the South Bend Railway in the fall of 1885, where several cars were equipped with small motors, and also in Minneapolis, where an electric car took the place of a steam locomotive. Other equipments were operated at the New Orleans Exhibition and at Montgomery, Alabama, where the current was at first taken from a single overhead wire which carried a traveling trolley connected to the car by a flexible conductor. Other equipments were put in operation at Windsor, Ontario, Detroit, Michigan, Appleton, Wisconsin, and Scranton, Pennsylvania. In these several equipments, the motors were placed on the front platforms of the cars and connected to the wheels by belts or chains. The cars were headed in one direction and operated from one end only. In 1888, the Van der Poel Company was absorbed by the Thomson-Houston, which had recently entered the railway field, and Van der Poel continued in its active development until his death in 1892. Among the early American workers of this period, none was for a time more prominent than Leo Daft, who, after considerable development in motors for stationary work, took up their application to electric railways, making the first experiments towards the close of 1883 at his company's works at Greenville, New Jersey, these being sufficiently successful to be repeated in November of that year on the Saratoga and Mount McGregor Road. The locomotive used there was called the Ampere and pulled a full-sized car. The motor was mounted on a platform and connected by belts to an intermediate shaft carried between the wheels, from which another set of belts led to pulleys on the driving axles. A center rail and the running rails formed the working conductors. Variation of speed was accomplished by variation of field resistance, this being accentuated by the use of iron instead of copper in some of the coils. In the following year, Daft equipped a small car on one of the piers at a New York seaside resort, and a little later another one at the Mechanics' Fair in Boston, the motor for this last being subsequently put on duty at the New Orleans Exposition. In 1885, work was begun by the Daft Company on the Hampton branch of the Baltimore Union Passenger Railway Company, where in August of that year operations were begun, at first with 2, and a year later with 2 more small electric locomotives which did not carry passengers themselves but pulled regular streetcars. A center and the running rail were used for the normal distribution, but at crossings an overhead conductor was installed and connection made to it by an arm carried on the car and pressed up against it. The driving was by a pinion operated on an internal gear on one of the axles. Daft's most ambitious work followed when a section of the 9th Avenue elevated road was equipped for a distance of 2 miles, on which a series of experiments were carried on during the latter part of 1885 with a locomotive called the Benjamin Franklin. The motor was mounted on a platform pivoted at one end, and motion was communicated from the armature to the driving wheel through grooved gears held in close contact partly by the weight of the machine and partly by an adjustable screw device. This locomotive, pulling a train of cars, made several trips, but the experiments were soon suspended. This work was followed by street railway equipments at Los Angeles and elsewhere, using double overhead wires carrying a trolley carriage. Meanwhile, Bentley and Knight, after some experiments in the yards of the Brush Electric Company at Cleveland in the fall of 1883, installed a conduit system in August 1884 on the tracks of the East Cleveland Horse Railway Company. The equipped section of the road was 2 miles long, the conduits were of wood laid between the tracks, and 2 cars were employed which were each equipped with a motor carried under the car body and transmitting power to the axle by wire cables. These equipments were operated with varying degrees of success during the winter of 1884 and 85, but were abandoned later. This work was followed by a double overhead trolley road at Woonsocket, the motors being supplied by the Thomson-Houston Company, and later by a combined double trolley and conduit road at Allegheny, Pennsylvania. In 1884 to 85, J.C. Henry installed and operated in Kansas City a railway supplied by two overhead conductors, on each of which traveled a small trolley connected to the car by a flexible cable. The motor was mounted on a frame supported on the car axle, and the power was transmitted through a clutch and a nest of gears giving 5 speeds. In the following year, a portion of another road was equipped. A number of experiments seem to have been conducted there, and on some the rails were used as a return. The collectors were of different types, and it is said that among others there was one carried on the car. The final selection was a trolley having 4 wheels disposed in pairs in a horizontal plane, carried by and gripping the sides of the wires. This feature, but using one wire and rail return, characterized a road installed by Henry in San Diego, California, opened in November 1887. Meanwhile, work had begun in Great Britain, where the first regular road to be put in operation was that known as the Portrush Electric Railway in Ireland, installed in 1883 by Siemens Brothers of London. Power was generated by turbines, and the current was transmitted by a third rail supported on wooden posts alongside of the track, the running rails constituting the return. The pressure used was about 250 volts. This was followed in the same year by a successful short road at Brighton, installed by Magnus Folk, the current being transmitted through the running rails. Then came the railway installed at Bessbrook, Newry, in 1885, under the direction of the Messrs. Hopkinson, and at Ryde in 1886, in which latter year was also installed the Blackpool Road by Holroyd Smith. In this latter case, the conduit system was used with complete metallic circuit. The motor was carried underneath the car between the axles and connected by chain gearing. Fixed brushes with end contact were used for both directions of running. Reverting to work in the United States, Sprague again took up the electric railway problem, and in 1885, before the Society of Arts, Boston, advocated the equipment of the New York Elevated Railway with motors carried on the trucks of the regular cars, and work was actually begun on the construction of experimental motors. Shortly afterward, a regular truck was equipped, and a long series of tests made on a private track in New York City. In May 1886, an elevated car was equipped with these motors, and a series of tests begun on the 34th Street branch of the road. These motors may be considered the parent models of the modern railway motor. They were centered through the brackets on the driving axles, connected to them by single reduction gears, and the free end of the motor was carried by springs from the transom, the truck elliptics being interposed between this support and the car body. The truck had 2 motors. They were run open, had 1 set of brushes, and were used not only for propelling the car, but for braking it. The motors were at first shunt-wound, but later had a correcting coil in series with the armature at right angles to the normal field to prevent shifting of the neutral point. The car was operated from each end by similar switches. Current at 600 volts was used, and increase of speed was effected by cutting out resistance in the armature circuit and then by reducing the field strength. This enabled energy to be returned to the line when decreasing from high speed. It being impossible to interest the railway management, the experiments were finally suspended. Soon afterward, a locomotive designed by Field had a short trial on the same section of the elevated. Sprague then turned his attention to building a locomotive car of 300 horsepower capacity, each truck to be equipped with 2 motors, each having a pair of armatures geared to the axle, but this evidently being ahead of the times, and the possibilities of street tramway traction becoming evident, these equipments were abandoned, and he began the development of the type of motor finally used in Richmond, one crude form of which was first used in storage battery experiments in Philadelphia and others in New York and Boston in 1886. Reviewing the conditions at the beginning of 1887, statistics compiled by T. Comerford Martin show that, including every kind of equipment, even those a fraction of a mile long and operated in mines, there were but 9 installations in Europe, aggregating about 20 miles of track, with a total equipment of 52 motors and motor cars, none operated with the present overhead line or conduit, and 7 cars operated by storage batteries, while in the United States there were only 10 installations with an aggregate of less than 40 miles of track and 50 motors and motor cars, operated mostly from overhead lines with traveling trolleys flexibly connected to the cars. These were partly Daft, but principally Vanderpool roads. Almost every inventor who had taken part in active work was still alive. The roads, however, were limited in character, varied in equipment, and presented nothing sufficient to overcome the prejudices of those interested in transportation and command the confidence of capital. As a result of all these experiments, the series-wound motor soon became universal because of its ability to start a car with the least expenditure of energy, and has held its place to the present time with minor improvements in its structure and method of gearing. 550 to 600 volts has become standard for the operation of the motors, this value having been found the most satisfactory. Although higher voltages are desirable for economy of transmission, the difficulties encountered in the construction of the motors offset any advantages gained thereby. As previously explained, the higher the voltage used, the further may the power be economically distributed. In the direct current system, the voltage is limited to about 600. With this comparatively low voltage, cars could be economically operated only within a few miles of the generating station. The development of the alternating current transformer, by means of which the voltage could be raised or lowered without mechanism, showed the way to new developments. The direct current generators in the power stations were gradually removed and alternators substituted. Power could be generated at either low or high voltages, stepped up by means of transformers sent over the line at a high voltage to a substation, dropped to a lower voltage again by the transformers, and changed to direct current by means of rotary converters, from which the car lines were fed. This is the system at present in use in all the large cities. The most unsatisfactory part of this system is the substation with its rotary converter, which increases the cost of the substation itself and requires considerable attention. One unfamiliar with the development of motors might ask why the cars were not equipped with alternating current motors. Motors of this class are, however, of quite recent origin, and their application to the severe strains of railway work has only been accomplished in the last 4 or 5 years. One of the most successful of these is the alternating current series motor developed by the Westinghouse Company, and it promises soon to be very widely applied. The outlook for equipping long railway lines heretofore operated by steam is very promising and in fact has already begun. In May 1905, the Westinghouse Company completed the first heavy locomotive to be operated by single-phase alternating current. This locomotive complete weighs 136 tons. It was built in 2 halves, each having 3 axles, each axle driven by a 225 horsepower single-phase series motor having single reduction gears with a ratio of 18:95. The current required to operate this locomotive, 6,600 volts, 25 cycles, is collected from the trolley wire by means of a pneumatically operated pantograph trolley with sliding contact and carried through an oil switch and circuit breaker to an autotransformer. In this transformer, it is reduced to 325 volts, at which pressure it is used in the motors. This locomotive, being designed for heavy freight service, develops a drawbar pull of 50,000 pounds at speed of from 10 to 12 miles per hour. Following several other successful applications of these motors, the New York, New Haven and Hartford Railroad decided to equip its roads as far as Stamford, Connecticut, a distance of 22 miles, with the Westinghouse system. The locomotives used weigh 70 tons and are each equipped with 4 gearless motors of 250 horsepower each. These locomotives operate over 12 miles of tracks in the city of New York by means of 600-volt direct current and over 22 miles of track supplied with alternating current at 11,000 volts, 25 cycles. Each locomotive is capable of hauling a 200-ton passenger train in accommodation service, requiring one stop every 2 miles at a scheduled speed of 26 miles per hour and a maximum speed of 45 miles per hour. In express service, a maximum speed of 60 to 70 miles per hour can be attained. Perhaps the longest line yet equipped is that of the Spokane and Inland Railroad, having a total length of track of 146 miles. It has been attempted to apply other forms of alternating current motors to railway propulsion. One of these is known as the repulsion motor, and although it has been tried on short lines, it does not as yet appear to have been so successful as the series type. This form has also been used in Germany, where some interesting tests on high-speed lines have been made, during which speeds of 140 miles per hour have been recorded, and 126 miles per hour with a car carrying passengers. End of section 28.
Section 29 of the Science, History of the Universe, Volume 3. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. The Science, History of the Universe, Volume 3, edited by Francis Rolt Wheeler. Electricity, Chapter 10, The Electromagnetic Telegraph, Part 1. As early as 1774, Lesage constructed an electric telegraph consisting of 24 wires, at the end of each of which was a pithball electroscope, and in 1816, Ronalds constructed a line of 1 wire using pithballs and 2 synchronous wheels. He endeavored to bring the matter to the attention of the British government and received the really exquisite reply that telegraphs of any kind are now wholly unnecessary, and no other than the one now in use will be adopted. A very important step was taken in 1828 by Harrison Gray Dyer of New York, who invented a method of recording in which a discharge was made to pass through a sheet of moistened litmus paper moving at a uniform rate. A line was actually set up and experimented upon in the same year. In all of these systems, it was proposed to use frictional electricity, but even with the present vastly increased power of production and control of this species of electricity, a successfully operating telegraph would hardly be possible. The real electric telegraph began with Galvani and Volta, and, as already intimated, more than one system has been fairly successful, the fundamental principles of which were understood before the close of the first decade of the present century. The complete solution of the problem, however, would unquestionably have been postponed for many years, but for the discovery of Oersted in 1820. Immediately on its announcement, the telegraph became the dream of many men in many countries. Concerning its origin and growth, says T.C. Mendenhall in his Century of Electricity, the great majority of Americans have been singularly mistaken. The popular impression seems to be that, It is exclusively an American invention, and that in America it was almost exclusively the product of the genius of one man. It hardly need be said that these impressions are extremely erroneous. Ampere, whose genius had accomplished so much in the early development of the theory of electromagnetism, was probably the first to suggest its use in telegraphy. His method was founded on Ørsted's experiment. If a needle could be deflected by an electric current, if this could be accomplished by a wire or wires of great length, and if these movements of the needle could be converted into a code by means of which letters or words could be expressed, then the electromagnetic telegraph was possible. Ampere's suggestion was to employ a number of wires and to deflect a number of needles. Considerable attention was given to the development of this idea for a number of years, following the discovery of its fundamental principle. The progress of the invention was seriously retarded by the publication of an investigation by Barlow of the Woolwich Military Academy in 1825, in the course of which he discovered that there was an enormous diminution in the power of a current to produce effects with an increase of distance, and which led him to declare that the project of an electromagnetic telegraph could not possibly be successful. The invention of the electromagnet by Sturgeon apparently offered a new solution of the problem, but, owing to the imperfect construction of his magnets, the difficulty of overcoming distance was not diminished. This obstacle, which seems for a time to be insurmountable, was conquered by Joseph Henry in the manner already described. Out of Ørsted's experiment grew the needle telegraph, a form which prevailed for several years in Europe, until it gave way before the evident superiority of that founded on the electromagnet, which grew out of the researches of Henry, and which is generally known as the Morse or American system. The needle telegraph was first in the field, and its working will first be considered. Many of its earlier forms appear as suggestions only, no attempt having been made to put them in practical operation. In 1832, however, Baron Schilling, a Russian counselor of state, had a working system in which 36 needles were used, and which included an ingenious alarm for calling the attention of the receiving operator. It consisted of a device by means of which the movement of one of the needles released a small ball of lead, which, by dropping upon the mechanism of the alarm, set it in operation. A model of this system was exhibited before the emperors Alexander and Nicholas. A little later, the two illustrious German philosophers, Gauss and Weber, established a successfully operating line at Göttingen. It was 2 or 3 miles long, and a double wire was used. Magnetic needles or bars, freely suspended, were used as receiving instruments, and the arrangement included a device for setting off an alarm clock. The current from a battery was first used, but afterward the secondary or induced current was substituted. This line was in working order in 1833 and was established mainly for experimental purposes. The practical development of the scheme was given over to Steinheil, in whose hands it grew with rapidity. In 1837, he had constructed several miles of telegraph, extending from Munich to various points in the vicinity. His work appears to have been officially sanctioned by the government, and his wires doubtless constituted the first electric telegraph ever erected for commercial purposes. The system included a method of recording the message as received, which might also be read by sound, the signals being distinguished from each other by the use of bells differing in pitch. But altogether the most valuable contribution made by Steinheil, says Mendenhall, was the discovery that the use of a double wire was unnecessary, it being possible to establish electric communication between 2 points by the use of one wire, whose terminals were joined to the earth through plates of metal or other conductors exposing considerable surface. As it largely reduced the cost of construction, this discovery was of prime importance. It was really a repetition of what Franklin had long before accomplished when he stretched his wire across the Schuylkill River, but the relation between the two experiments was not at the time appreciated or fully understood. Both the science of electricity and the art of telegraphy owe much to the genius of Sir Charles Wheatstone, whose interest in and connection with telegraph enterprises began in 1835, in which year he exhibited one of Schilling's telegraphs in his lectures, and in the year 1837, when he formed a co-partnership with W. F. Cooke for the purpose of introducing the electric telegraph into England. Their first patent was taken out in 1837, and the system required 5 needles, with as many wires for their manipulation, and a 6th wire for the return current. Wheatstone developed numerous improvements during the next few years, and as early as 1840, a dial instrument showing the letters of the alphabet was patented. Numerous difficulties were encountered and overcome, and by 1844, the enterprise was on a sound financial basis. The operation of working a telegraph was at first naturally regarded by most people as a mystery and by many as a fraud. When communication was established between Paddington and Slough, a distance of about 20 miles, the wires were insulated partly by silk and were suspended through goose quills attached to posts along the Great Western Railroad. The telegraph company not only invited the patronage of the public in a legitimate business way, but it also exhibited its apparatus as a novelty. This short line speedily established itself in the good graces of the people through its instrumentality in securing the arrest of a criminal. The construction expenses incident to the use of a large number of wires, to say nothing of other difficulties, led to the reduction of the number of needles employed to 2, and 1 in which a single wire was sufficient. A single needle is now almost universally employed wherever the needle system has survived competition with other forms. The movements of the needle are readily applied to signaling the alphabet by combinations of swings to the right and to the left. It will be remembered that in Oersted's experiment, a reversal of the current through the wire reversed the direction of the deflection of the needle. The operating key is so arranged that when its handle is turned to the right, a current is sent through the line which deflects the needle in the same direction, and when the opposite movement is made, the current is reversed and the needle swings to the left. The alphabet may and generally does correspond with what is known as the Morse code. A swing to the right is interpreted as a long signal or dash, and one to the left as the short or dot signal of the Morse system. For many years, the needle system of telegraph was used almost exclusively in Great Britain, although it never succeeded in gaining a foothold on the continent of Europe or in any other part of the world. Its principal advantage is the comparatively feeble current required to work it, but it is slower than the Morse system and does not lend itself to sound reading or to methods of securing written records of the messages which it transmits. It has therefore almost entirely given way to other systems, even in Great Britain, although, as will be seen, it is retained in connection with long ocean cables, and within a few years, a self-recording device has been successfully applied to it. The system of telegraphy now almost universally in use is one which originated in America and whose development was nearly contemporaneous with that of the needle system. In England, the fundamental experiment about which the telegraph grew was that of Oersted, while in America, the electromagnet, as constructed by Sturgeon and improved by Henry, was made the basis of the invention. As there has been much misunderstanding concerning the distribution of credit for the evolution of this system of telegraphy, it may not be out of the way to consider at some length its important phases. Much credit must always be accorded Professor S. F. B. Morse, through whose indefatigable labors and persistent faith the commercial value of the enterprise was first established. Born in the last century, he reached the age of 40 years before having apparently given a single thought to what was to be the great work of his life. His early training was that of an artist, although he was always fond of scientific pursuits. He studied in London under the best masters, and was highly successful in his chosen profession, some of his works bringing him great renown. His first conception of an electromagnetic telegraph seems to have arisen out of a conversation with a friend on board the packet ship Sully, a voyage from Havre to New York in 1832. In this conversation, some experiments of the French were described, in which electricity had been transmitted through long distances. Someone remarked, "It would be well if we could send news in this rapid manner." To which Morse at once replied, "Why can't we?" And from that moment, he devoted his energies to accomplishing the desired end. During the remainder of the voyage, he made drawings of forms of apparatus and considered the transmission of signals into an alphabet. He does not appear to have been familiar with the principles of electromagnetism at that time, and it is affirmed that the use of an electromagnet was suggested to him by the gentleman with whom this first discussion was held. On reaching New York, he began experimenting upon the subject, and in 1835 he had completed a working model of his recording instrument. It was not until 1837, however, that he was able to put two of them in operation at the extremities of a short line, so as to be able to both receive and send signals. In that year, his apparatus was exhibited to many people in the University of New York. In the following year, he made an unsuccessful effort to secure aid from Congress to establish an experimental line between Washington and Baltimore. He then visited Europe, but failed to secure patents for his inventions. During the session of Congress of 1842-43, he again struggled to secure recognition and an appropriation to enable him to build his experimental line. The scheme was considered quixotic by many members of Congress, and at the last moment he despaired of success. But during the midnight hour of the last night of the session, March 3, 1843, a bill was passed appropriating $30,000 for the line from Washington to Baltimore. In the meantime, many apparently insuperable obstacles had been encountered in the attempt to secure the successful working of the apparatus. In the beginning, Morse used a magnet with a few turns of wire, as Sturgeon had done, and a single cell of battery. With this, his instrument failed to work through more than a few feet of wire. This difficulty was surmounted by taking advantage of the researches of Henry, using what he called an intensity magnet and many cells of battery instead of one. Although by this method signals could be transmitted through a comparatively long distance, they were still too feeble to print themselves upon the moving strip of paper. To overcome this difficulty, it was only necessary to introduce the device known as the relay, by means of which the work on the main circuit was reduced to making and breaking the current of a local battery, on the circuit of which was the recording machine. In this short circuit, the current was easily made strong enough to operate the registering instrument. This method of working had been devised nearly 10 years before by Henry, and it had also been used by Wheatstone in his needle system. In Morse's first attempt to build his experimental line from Washington to Baltimore in 1844, the wires were placed underground instead of upon poles, but the former method was soon abandoned for the latter, which had already been in use for several years in Europe and elsewhere. In Morse's first instrument, the transmitter was mechanical. That is to say, the message to be sent was first set up in dots and dashes by arranging long and short type in proper order in a line, and by the regular movement of this line of type, the current was closed for periods of time necessary for the reproduction of the dots and dashes at the other end. Morse did not imagine that signals could be made by the hand with sufficient regularity to produce legible records. This was soon discovered to be possible, however, and for the clumsy mechanical transmitter, the simple key in use today was substituted, by the skillful manipulation of which the operator produces dots and dashes with such regularity and rapidity as to leave nothing to be desired. The statements made above, derived from papers of an official character, may be summarized as follows. In the Morse telegraph are found the battery, for which credit must be given primarily to Volta, and then to Daniel, who in 1836 devised a battery nearly constant in its strength, an essential requisite to its application to the telegraph, the key or transmitter, which, except in details of construction, is practically that in use since experiments on electricity were begun, the receiving instrument, of which the essential feature is the electromagnet, due primarily to sturgeon, but modified and improved so as to be available for this work by Henry. The relay, by means of which the local current is put in operation, which was used by Henry and also by Wheatstone, the line wire suspended on poles, a method first practically used by Dr. W. O'Shanassy at Calcutta in 1839. While it appears, therefore, that Morse cannot justly claim priority in the discovery of a single scientific principle involved in the telegraph, it must be admitted on all hands that he played a most important part in its development. In Europe, all effort had been in the direction of the use of the needle system. Morse was quick to see the advantages of the electromagnet, and especially the ease with which it could be made to leave a permanent record of the message. His use of a simple armature with to and fro motion, armed with a style or pencil, which marked long or short lines upon a moving slip of paper, and his alphabet, made up of these dots and dashes, show great ingenuity and mechanical judgment. As a measure of the value of his system compared with the English, it is sufficient to repeat that today it has driven nearly every other from the field. End of section 29. Section 30 of the Science, History of the Universe, Volume 3. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. The Science, History of the Universe, Volume 3, edited by Francis Rolt Wheeler. Electricity, Chapter 10, The Electromagnetic Telegraph, Part 2. As the popularity of the telegraph increased and the number of line wires grew large, attempts were made to make one line wire transmit more than one message at the same time. Various schemes have been tried, most of which have failed by reason of the complications of the apparatus and the subsequent troubles attending them. The step in the direction of utilizing the line wire more fully was the invention of the duplex system by Dr. Wilhelm Ginthel in 1853. This system was improved by Carl Frischken of Hanover until it lacked only one essential element, means to overcome the condenser-like action of the long line wire. It was not until 1872 that this was supplied by Joseph B. Stearns of Boston, who introduced a condenser into the artificial line of the duplex system, and by adjusting it, made the artificial line behave like the line wire itself. This important addition made the system entirely successful, so that it became possible to transmit two messages in opposite directions at the same time. Following the success of the duplex system, there was developed a method by which two messages could be sent simultaneously in the same direction, and it was but a step to combine these two systems so that two messages could be sent each way simultaneously. This last is known as the quadruplex system and was immediately successful because there were no delicate adjustments to be made and no rotating parts as in some of the synchronous telegraphs which have been tried from time to time. As early as 1852, Moses G. Farmer of Salem, Massachusetts, devised a synchronous multiple telegraph in which he proposed to employ two rotating switches, one at each end of the line, to successively and simultaneously join the several operators at one station with those of another. The idea was to connect two operators for an instant, pass on to the next two, and so on, returning to the first two operators so quickly that the relay of the receiving operator would not have had time to change, nor the key of the sender to make a dot. The impulses of the current had therefore to be made with great frequency, and the control of this impulsive current was the principal cause of failure. Another difficulty was the maintenance of the rotating switches in synchronism. The public is occasionally startled with an announcement that someone has invented a telegraph by which a wire may be utilized for 20 or perhaps 40 transmissions, but usually it is the old wanderer in a new garb. Speed by this method, however, is limited far within the bounds of these statements. It might seem that it would be only necessary to multiply the number of contacts and to increase the velocity of the rotating arms, But the limit in this direction is soon reached, for only a certain number of impulses can be transmitted over a line within a certain period with force sufficient to produce signals. Many valuable improvements have been made in recent years in this class of telegraphy, but large as the art has grown, the great object of all has been to obtain more perfect synchronism, that is to say, to cause two mechanically independent arms to rotate at the same speed. One of the most recent of these synchronous telegraphs, and which is now being exploited, is that invented by Mr. Delaney. The principle is that of Farmer, but the method used to hold the rotating switches in synchronism is extremely ingenious. It is stated that 1,000 words per minute may be transmitted over a single wire. The messages are prepared on a tape by a punching machine and received on a chemically prepared strip of paper. The idea of printing the dispatch is not new. In the early days of the electric telegraph, 1841, Wheatstone took out a patent for printing the message in ordinary letters upon a strip of paper. Since then, many inventors have followed out the same idea, with more or less success. The most perfect of all these systems, however, is that invented by Professor David E. Hughes, which, in a modified form, is now very generally used as a news or stock ticker. Figure 45 shows the connections for such a telegraph. The sending station is at A, and one of the receiving stations is at B. The line is fed with an alternating current produced by reversing commutator 4. This alternating current does not affect printing relay 5, but does operate polar relay 6, which in turn operates the escapement. Reverser 4 is driven by constant speed motor 1 and has as many segments as there are characters on the type wheel. The escape wheel 10 is provided with an equal number of teeth, so that each revolution of reverser 4 will produce one revolution of type wheel 7. On the shaft with the reverser is rigidly mounted a cylinder, provided with a number of pins, arranged spirally as shown. Each pin is in line with a segment of the reverser, and also in line with a pin fastened to the keyboard. Depressing a given key will always stop the cylinder, and therefore type wheel 7 in the same place. The connection to the motor 1 is made with friction clutch 2, which slips when cylinder 3 is stopped. Now it is evident, if type wheel 7 is started with its characters in certain position and is rotated by a motor through gear 11 and controlled by escapement magnet 6, that it will always remain in the same relative position with cylinder 3, and that the operator can stop the type wheel in any desired position. If the type wheel stops because of the arrest of the cylinder 3 by depression of a key, the current ceases to alternate, and magnet 5 has time to draw up its armature, 8, and press the tape against the type wheel, thus printing the character which corresponds to key depressed at the sending station. These are ingenious arrangements for reproducing at a distant point handwriting, drawings, etc. One of the first of these is known as Caselli's pentelegraph, because the reproduction may be of the same size or even larger than the original. The message to be sent is written with an insulating ink on a piece of tinfoil and received on a sheet of chemically prepared paper, upon which a blue dot is left at each current impulse. The motions of the marking style at the two stations are controlled by similar pendulums. In the Denison system, these pendulums are forced to vibrate together through the control of electromagnets operated by the same alternating current. The most recent and useful of these arrangements is the telautograph. The message is reproduced as fast as it is written. Drawings or sketches are transmitted with great accuracy. In fact, every motion of the sending pen is instantly followed by the receiver. Some of these are in use in the United States Army. The insulation of conductors for use underwater was made possible by the discovery of gutta percha by an English surgeon in India in 1842. It is extremely probable that the widespread use of submarine cables would have been postponed many years had this substance remained unknown. One of the first cables insulated by this material, and possibly the very first, was laid in 1848 across the Hudson River from Jersey City to New York. In 1850, a cable was laid across the channel from Dover to Calais but it was unprotected by any sheathing or armor, and it lasted but a single day. In the following year, the experiment was repeated, this time with a cable protected by a number of heavy iron wires. The operation was successful, and permanent telegraph communication was established. During the next few years, the number of submarine cables increased rapidly, as did also their length, although on account of ignorance in regard to many conditions necessary to ensure the best success, failures were numerous. Many people began to consider the feasibility of a line connecting the continents across the Atlantic Ocean. A few sanguine capitalists combined to further the enterprise, and through the undaunted courage and faith of an American, Mr. Cyrus W. Field, the purely financial obstacles were surmounted. Unfortunately, the electrical and engineering problems to be met with were not understood, and the first cable of 1858, after gasping for breath for a few short weeks, lay dumb forever at the bottom of the sea. Something of the character of this cable may be learned from the following brief description by Sir William Thomson, to whom, more than to any other one man, the world is indebted for the success of submarine telegraphy. In the year 1857, as much iron as would make a cube 20 feet wide was drawn into wire long enough to extend from the earth to the moon and bind several times around each globe. This wire was made into 126 lengths of 2,500 miles and spun into 18 strands of 7 wires each. A single strand of 7 copper wires of the same length, weighing in all 110 grains per foot, was 3 times coated with gutta percha to an entire outer thickness of 0.4 of an inch, and this was served outside with 240 tons of tarred yarn, and then laid over with the 18 strands of iron wire in long continuous spirals and passed through a bath of melted pitch. An attempt to lay this cable in 1857 resulted in the loss of 400 or 500 miles by breaking from the stern of the ship from which it was run. After some further experimentation, it was determined to employ 2 ships to lay it in the following year, and accordingly, on the 29th of July, 1858, the Niagara and the Agamemnon, each loaded with half the cable, met in mid-ocean, joined the ends, and started, the Niagara for the west and the Agamemnon for the east. On the 5th of August, the ends were successfully landed on the opposite shores of the Atlantic. The cable was known to be in bad condition before the laying was completed, and the earnest but ill-advised efforts which were made to force it to work during its brief period of activity only tended to shorten its life. Communication of a very irregular and unsatisfactory character was maintained for several weeks. The admirable mirror galvanometer, which had just been devised by Sir William Thomson, was for the first time in use at the Valentia end, while for a time the attempt was made to use the ordinary receiving apparatus which had been provided by the company at Newfoundland. Later the galvanometer was put in use on this side, but not before very powerful currents had been used on the cable. In fact, Sir William Thomson has declared his belief that, if proper methods of handling the cable electrically had been in use from the beginning, its performance would have been lasting and in the main satisfactory. Owing to the fragmentary character of many of the messages transmitted, a single sentence from that of the Queen to the President having been received on August 16th, and the remainder 24 hours later, many persons in both Europe and America became skeptical as to the transmission of signals, and not a few even doubted that the cable had been laid. As a matter of fact, 400 messages containing over 4,000 words were sent. On September 1st, interchange of messages ceased, but on October 20th, the cable spoke its last words, 240, which were read at Valentia, being part of a message giving the number of battery cells then on the line. From that date, the splendid combination of matter lay at the bottom of the sea, forever useless. But it had not lived in vain. The possibility of the thing was demonstrated, and it only remained to surmount the obstacles which this trial had shown. During a few years succeeding this first attempt, The problem was studied in the light of the experience which it had afforded. Another trial was made in 1865, this time by the Great Eastern, a vessel which offered many advantages for cable laying. After about 2/3 of the distance was run, the cable broke, and further operations were postponed until the following year, when a complete cable was successfully laid, and that of 1865 picked up, spliced, and finished. Since then, other lines have been placed across the Atlantic, and now the operations of laying an ocean cable attracts no attention. One of the difficulties encountered in attempting to send messages through such a long cable was that due to the electrostatic capacity of the cable. The cable acts like a very large condenser, so that when the voltage is applied at one end, the current does not instantly rise to its steady value, but takes several seconds, and when the supply of voltage is disconnected, the current continues to flow. In order to signal rapidly, therefore, it was necessary to overcome this action and to use very delicate receiving instruments. For this purpose, Sir William Thomson, Lord Kelvin, devised the well-known siphon recorder, which is really a sensitive galvanometer, whose moving coil carries a siphon tube filled with ink, the ink being ejected from it in fine drops on a strip of paper. To produce these fine drops, the siphon tube is connected to a small electrostatic machine, so that the tube is electrified. Although the telephone has made such rapid advances as a means of communication, the telegraph still holds its own field. The greater simplicity of the latter, the less expensive lines, the greater distances to which messages can be transmitted, all combine for its preservation. The flattening out of the waves on a telephone line, due to the condenser-like action of the line, has not yet been overcome. The difference between the telephonic waves at the beginning and end of a line may be compared to that between the noisy exhaust of an automobile motor, without and with a muffler. In the case of the transmission of telephone waves, it is therefore a problem of how to rid the line of its muffler. End of section 30.
Section 31 of The Science History of the Universe, Volume 3. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Amelia Chesley. The Science History of the Universe, Volume 3, edited by Francis Rolt Wheeler. Electricity. Chapter 11, Wireless Telegraphy, Part 1. Professor Henry of Princeton University was the first to show the oscillatory character of the discharge of a Leyden jar. This single loud spark, which to the eye seems to pass in one direction across the gap, is really a quick succession of current surges, first one way and then the other, and has its mechanical analogy in the pendulum. At the outset, it may be well to analyze this spark discharge, as it is still the most prominent means of radiating the electric waves used to transmit signals. Suppose this pendulum analogy of the spark discharge between two spheres be taken, and the similarity of the two actions noted. If a heavy pendulum be drawn back by means of a light fiber, it will finally strain the fiber to such an extent as to cause it to break. The pendulum, being suddenly released, gradually acquires motion, which is accelerated until its lowest position is reached, after which it is retarded just as it was accelerated, and stops at about the same height at which it started. The process is then repeated, but in the opposite direction. Now compare the action on the two charged spheres. The pressure in the dielectric surrounding the spheres is gradually raised until it suddenly gives way, there being a flow of current from the positive to the negative sphere, which current gradually increases and is greatest at the instant when both dielectrics are at the same potential, just as the motion of the pendulum was greatest at its lowest position. The current then begins to decrease and finally stops when the dielectric is again strained to about the same potential it had at first, but reversed in direction. The current then starts back again, just as the pendulum again required motion. Now let it be considered what goes on in the space surrounding this action. A current is always surrounded by a field of magnetic force, which field is proportional to the strength of the current. As this current between the two spheres increases, there is, therefore, sent out an increasing magnetic field which is radiated into space, reaching a maximum and again decreasing with the current. But while the current increases, the electrostatic strain about the sphere decreases, thus sending out an electrostatic wave, which again increases as the current decreases. It will thus be seen that as these surges take place, alternate electromagnetic and electrostatic waves are radiated into space. Why do not these surges keep on forever? Mainly because the current in its flow across the gap encounters a resistance, and instead of converting all its energy into magnetic waves, loses a portion as heat at each surge. This corresponds to oscillating the pendulum in a liquid or viscous material, the energy of its motion soon being converted into heat. So much for the creation of these waves, but how may their passage through space be detected? One way is by catching them on a wire. What is the manner of the catching? If a wire be placed so that it cuts the wave transversely to its line of motion, it is clear that the moving magnetic wave will induce in it an electromotive force. As these waves follow in rapid succession, a series of alternating electromotive forces is set up in the wire. These oscillatory currents are sometimes called jigs. How these jig currents make their presence known varies with the style of wave detector used. Before entering upon the history of this spark telegraphy, as the Germans call it, it may be well to review some of the experiments which preceded this system. In 1838, Professor Joseph Henry of Princeton, making with an electrical machine and Leyden jar a 1-inch spark in the top room of his residence, set up induced currents in the cellar of the same building. Professor Morse, however, was probably the first to successfully transmit signals without wire. On December 16, 1842, he sent a wireless telegram across a canal 80 feet wide, and in November 1844, L.D. Gale, acting under instructions from Professor Morse, made wireless signals across the Susquehanna River at Havre de Grace, a distance of nearly 1 mile. In the latter experiment, Mr. Gale used as a source of energy 6 pairs of plates in the form of a galvanic battery. He found that the best results were obtained when on each side of the river 2 plates were immersed near its bank and were connected by an insulated wire stretched along each shore for a distance 3 times as great as that which measured either path of the crossing signals. A few years later, James Lindsay, a Scotchman, repeated Morse's experiments but without knowing of them. In 1859, he read a paper before the British Association on the subject of telegraphing without wires, and among his hearers were Faraday and Lord Kelvin. A method of signaling without wires by means of the inductive effect of 2 parallel circuits was successfully used by Sir William Preece in 1882. The principle of this method is as follows. If 2 loops of wire are placed parallel to each other and an intermittent current is passed through one of them, waves of magnetic flux are sent out, portions of which thread the second loop and by their fluctuations produce currents in it which may be detected by a telephone or other device. The strength of such signals falls off very rapidly from the source, and such a system can only be made to operate over short distances. Preece constructed 2 parallel lines, one on the English coast and one on the Isle of Wight, the arrangement of which is shown in Figure 48. It will be seen that the loop from which the waves emanate is formed by the line wire and the earth. The crowning achievement, however, was the work of Hertz, whose early death deprived the world of the aid of a most powerful brain. In 1886, Hertz discovered that if a loop of wire having a small air gap left in it were placed at a distance from a spark discharge of a Leyden jar, minute sparks would pass across the air gap of the loop, thus indicating the presence of electric waves. He subsequently made a very complete study of the behavior of these waves and thus gave a tremendous impetus to the development of wireless telegraphy. Second to the work of Hertz is that of Sir Oliver Lodge, who in 1889 discovered the effect of electrical waves on the breaking down of the electrical resistance of 2 knobs barely in contact, which discovery resulted in the first means used to detect the presence of electrical waves, the coherer. The development of wave detectors is an important chapter. For these instruments, Professor Fleming has suggested the use of the word cymoscope as a general term including all classes of wave detectors. A great number of these have been invented, but they may all be included under the following classes. 1. Spark simoscopes. 2. Contact simoscopes. 3. Thermal simoscopes. 4. Magnetic simoscopes. 5. Electrolytic simoscopes. 6. Electrodynamic simoscopes. And 7. Vacuum tube simoscopes. The first simoscope invented was that used by Hertz in his investigation of electrical waves, and belongs to the first class. It consisted merely of a ring broken at one point and arranged so that the gap might be adjusted by means of a micrometer screw. Tiny sparks across this gap indicated the presence of waves. Since the electromotive force required to produce a spark across even a small gap is very considerable, it will be obvious that such a detector could only operate at a short distance, and would therefore be useless for the purpose of signaling. The next invention, made in 1890, was the Bramley coherer, figure 49, which consisted of a small glass tube containing two metallic plugs and separated by a gap partially filled with metallic fillings. This is an example of the second class. The metallic fillings, when loosely packed, offer a very high resistance to the passage of current through them, but the presence of waves breaks down their contact resistance, which continues after the waves have ceased. In order to again restore their resistance, they must be tapped or shaken, an operation known as decoherence. It is obvious that such an apparatus may be used like a key in a telegraph circuit, a key operated by electrical waves, and may therefore be used to operate a telegraphic instrument. Such was the first device used. It was defective, however, in that it was necessary to tap it after each signal. Decoherence was not certain, it required frequent adjustment, and the result was often a confused lot of signals. Many arrangements of loose contacts were tried, and the coherer was improved by Marconi, Lodge, Braun, and others. One of the principal troubles being the operation of decoherence. Most of the inventors sought to develop a coherer which could be self-restoring, and a number of successful types were invented. One of these was the Hughes coherer, employing carbon granules placed between iron plugs. The most perfect and successful of all these is, however, that devised by Sir Oliver Lodge and Dr. Muirhead, and used in the Lodge-Muirhead system. As shown in figure 50, it consists of a steel disc slightly separated from a globule of mercury by a film of oil, the disc being arranged to rotate slowly. The presence of waves breaks down the oil film and establishes contact with the mercury, which contact immediately breaks upon the cessation of the waves. A siphon recorder, placed in series with the simoscope, is used to record the message. Although a number of forms of magnetic style of detector were devised, it was not until 1902 that a successful working apparatus was produced. For some time before that, it was known that the oscillating currents received would annul wholly or in part the magnetic hysteresis of iron when passed through a coil surrounding the iron. Hysteresis acts like molecular friction, so that when a magnetizing current is passed through a coil surrounding an iron core, the magnetization does not increase and decrease with the current in the coil, but lags behind it. If another coil be placed around this same core, and the oscillating currents passed through it, this hysteresis will be suddenly removed, and the magnetism in the core will suddenly change in value. This sudden change could be detected by a third coil surrounding the core and connected to a telephone receiver, resulting in a sudden click. This was the principle of which Marconi made use in his magnetic detector, and which he has used in his long-distance experiments. The arrangement is shown in figure 18. It consists of a band of iron wires passing through two coils, one carrying the jig currents and one connected to the telephone. The wires are magnetized by two permanent magnets, and as they move under that portion where the two poles meet, the magnetic flux in them undergoes a reversal, which reversal, however, always takes place at the same point until the jig currents pass, when the flux is suddenly shifted backward, causing a sound in the telephone. These detectors have come into very general use on account of their convenience, sensitiveness, and adaptation to rapid signaling. In 1901, Dr. Lee de Forest patented a detector which depends for its operation on the disruption of the minute metallic bridges or trees which form under suitable conditions between the electrodes of an electrolytic cell. The apparatus, called a responder, consists in a glass tube similar to that of a coherer, in which are fitted 2 electrodes, preferably of tin. The space between the electrodes, about 1/64 of an inch, is filled with a viscous semiconducting liquid such as glycerin with a small admixture of water, together with some peroxide of lead as a depolarizer to prevent the excessive evolution of gas. When a cell of suitable voltage is connected across this responder, metallic trees or bridges are formed which make a path of low resistance, but upon the passage of the jig currents these trees are broken down and the circuit broken, producing a sound in a telephone receiver. Immediately upon the cessation of the jig currents, however, these trees again establish themselves. Another very successful and extremely sensitive detector was invented by Fessenden and Freeland, and consists of a small platinum cathode containing nitric acid with a minute anode of platinum wire 1/10,000th of an inch in diameter. This little electrolytic cell, when polarized to the critical point by being connected to a battery, is remarkably sensitive to jig currents. It has been employed by Fessenden in his transatlantic experiments. Many other detectors have been developed which have operated successfully, but those described are used most generally. It would not be possible in a few words to give a comprehensive idea of the various systems in use, as many important improvements which have been made in the last 10 years. Those systems which have attained commercial importance are the Marconi, the Fessenden, the De Forest, the Slaby-Arco, and the Lodge-Muirhead. The greatest differences are usually found in the receiving apparatus. The first system used by Marconi employed the coherer as a wave detector and the Ruhmhorff coil to produce the sparks from which the waves were radiated. The diagrammatic arrangement of the sending and receiving apparatus is shown in Figure 52, T being the coherer and L the telegraphic relay. Experiments with this form of apparatus were first made in 1896 in England, where Marconi went to obtain the assistance of Sir William Preece. These experiments were so successful that trials were made during the next year, at each of which something new was learned, whereby the distance of transmission was increased. From some of these experiments, Marconi worked out the effect of the height of the antenna or aerial wire on the distance of transmission. In August 1897, Marconi organized a company known as the Wireless Telegraph and Signal Company, with a capital of $5 million. In June 1897, Marconi went to Rome, and after having undertaken in this city at the instigation of the Minister of Marine several experiments from one floor to another with a conductor 3 yards in height, was invited by the Honorable Bryn, Minister of Marine, to undertake, in the presence of a select commission composed of officers who were specialists belonging to the Royal Marines, some fresh experiments. The place chosen was the Gulf of Spezia. The experiments took place between the 11th and 18th of July, 1897. The apparatus made use of for transmitting and receiving was similar to those employed on the Bristol Channel, that is to say, aerial wires ending above in metallic sheets. The coil was less powerful than that used in the former case, giving sparks 10 inches in length only. The apparatus was located during the entire series of experiments in the electrical laboratory of St. Bartholomew and bore an aerial line about 75 feet in height, which was afterward prolonged to 90, terminating in a square metal sheet of about 8 feet in the side. On the first 3 days, the 11th, 12th, and 13th of July, the experiments were executed on land, which gave very good results up to a distance of 3.5 kilometers, or say 2 miles. On the 14th of July, the receiver was set up on board a tug having a mast about 50 feet in height, which bore an aerial wire of equal length ending in a sheet about 8 feet in the side. The transmitting station was bound to carry out the following instructions. 10 minutes after the start of the tug, it was to send for 15 minutes dots and dashes at intervals of 10 seconds. Then transmit a phrase, maintaining between each signal an interval of 10 seconds. Then to suspend transmission for an interval of 5 minutes, after which it should go through the same round, but with intervals of 5 seconds instead of 10 between each signal. The tug having started from the little port of St. Bartholomew, the receiver registered some signs even before transmission had begun on land, a fact due doubtless to extraneous causes. She directed her course toward the western mouth of the mole and continued to receive signals, not, however, in the order and in the intervals that had been prearranged, but much more frequently. The sky was covered with stormy clouds, and in the distance lightning was frequent. Hence it was surmised that besides the signals that were really transmitted, others, due to atmospheric influence, were impressing themselves, which rendered the strip of paper on which they were registered illegible. On again repeating these experiments after the storm clouds had disappeared, correspondence came out very clearly up to a distance of 5,500 meters, nearly 3 miles, with the tug stationary. The tug was again put in motion so as to interpose between itself and the station of St. Bartholomew the point called Le Castagne, in order to ascertain what effect such a screen would have on signaling. The signals ceased as soon as the obstacle intervened, to recommence on the tug being moved from its influence. On the return journey, the messages continued to come out clear and exact. On the 17th of July, trials were made from the same stations of St. Bartholomew to the armored ship San Martino, anchored at a distance of about 1 3/4 miles from the transmitting station, the aerial conductor of which had been carried to a height of about 40 yards, while the ship bore at the receiver an aerial line first of 20 and then of 30 yards in height. Transmission succeeded perfectly, independent of the position of the coherer and the receiver. That is to say, even if they were screened at the sending station and surrounded by metallic masses under cover or placed below the waterline in the ship. End of section 31. Section 32 of The Science History of the Universe, Volume 3. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Amelia Chesley. The Science History of the Universe, Volume 3, edited by Francis Rolt Wheeler. Electricity. Chapter 11, Part 2. It was at once foreseen by many experimenters, among them Sir Oliver Lodge, that with the old forms of apparatus there would be interference between wireless stations, as the receivers would respond to all wavelengths. To understand how it is possible to make a sending or a receiving circuit which will send out or respond to only one kind of electric wave, let the pendulum analogy again be used. In order to set a pendulum in motion, it is necessary that the impulsive force should be imparted to it the same number of times per second in which the pendulum naturally oscillates. Even if stray forces are applied, but are not properly timed, the effect on the pendulum will be small, whereas a very minute but properly timed force, acting for some time, will produce considerable motion in a large pendulum. All these characteristics of the pendulum may be applied to the electric circuit: the natural period of vibration, the small effect of a lot of waves differing in length, and the large effect of a succession of feeble but similar waves. Sir Oliver Lodge in 1897 took out a patent for a syntonic system of wireless telegraphy, based directly on his own work on the discharge of Leyden jars and on Hertz's experimental results. The transmitter consisted of 2 large cones of sheet metal placed with their axes in a vertical line, and having a spark gap between their apices. In another form of transmitter, a single metal sphere separated by small spark gaps from the terminals of an induction coil was used as a radiator. Both types produced direct Hertzian radiation, the latter giving waves of very high frequency. The spherical oscillator was partially enclosed by a copper cylinder, open at one end in order that the rays might be condensed in one direction. The receiver, for use in connection with the large cones, consisted of 2 smaller cones connected through the primary of a small transformer, the secondary of which was connected to the coherer circuit. The dimensions of the transmitter and receiver were adjusted to give equifrequent natural vibrations and therefore resonance. No earth connection was made, as it was desired that the transmission should be purely by means of free radiations. The early conical form of radiator has now given place to the horizontal conductors. Stations in which this latter arrangement has been adopted are now working in various parts of the world. As soon as Marconi had modified his system of telegraphy, he applied it immediately to the conquest of record distances in radiotelegraphic transmission. To this end, he set up a station at the Lizard, Cornwall, which was immediately put into communication with Marconi's experimental station at St. Catherine's, Isle of Wight, at a distance of 300 kilometers, about 200 miles, in which he used an aerial conductor consisting of 4 vertical wires standing about 5 feet from one another, about 144 feet in height, along with a strip of wire netting of the same length. Under the new system, the energy required to telegraph to a given distance was very much diminished, so that 150 watts sufficed to communicate to the 300-kilometer distance. Encouraged by the results of the experiments in communication between St. Catherine's and the Lizard, Marconi put his whole heart into the attempt to resolve the arduous problem of establishing transatlantic radiotelegraphic communication. Repeated experiments had shown that long waves, either by successive reflection or diffraction, could turn round the surface of the Earth, so that their transmission to very great distances resolved itself only into a question of sufficient power in the transmitting apparatus and sufficient sensibility in the receiving. But these necessitated large financial means, which would, however, not be wanting in a man whose business acumen was not less surprising than his experimental ability. Being largely subsidized by the Marconi Wireless Telegraph Company, Marconi began early in 1901, unknown to everyone, his trials, by establishing 2 specially powerful stations at Poldhu near Cape Lizard in Cornwall, on one side of the ocean, and at Cape Cod in Massachusetts on the other side. The results of these first trials are not known, and judging by the silence maintained in this regard, they were probably negative. The 2 stations, that had cost the sum of more than £15,000, were destroyed by storms in September of the same year. Marconi caused the station at Poldhu to be rebuilt, furnishing it with powerful machines and radiators, and decided to attempt communication with St. John's, Newfoundland, that is to say, to a lesser distance than that previously chosen, of about 1,500 miles. At St. John's, Newfoundland, where Marconi had obtained from the government every facility for making the trials, the installation was of the simplest character, consisting of a receiving station only. The aerial line was maintained at a height of about 400 feet by means of a kite. Marconi had already agreed with the station at Poldhu that every day at 6 o'clock in the evening a long series of letter S should be sent. This letter, in the Morse alphabet, consists of 3 dots. The message was received telephonically. On the 12th of December 1901, Marconi announced that he had received the different S's at equal and determinate intervals, and he proclaimed that it was practically, physically, and mathematically impossible that the signals could have come from any other place but Cape Lizard. In the summer of 1902, Mr. Marconi made an interesting comparative test of his first coherer system and his second magnetic detector system. The ship Carlo Alberto was fitted out with both sets of receiving apparatus. By previous arrangement, a set of signals from the Poldhu station was to be sent out at certain hours of the day. As the voyage towards Kronstadt proceeded, the signals diminished in strength, and at a distance of 900 kilometers were not perceptible during the day. At night, however, they continued to be received by both systems until the port of Kronstadt was reached, when only the magnetic detector responded, and that only feebly. The disturbing action of daylight was very marked in these tests. Having received an invitation from the Canadian government to continue his experiments in Canada, Marconi erected a large station at Tablehead, on the island of Cape Breton, at the mouth of Glace Bay, and 3,800 kilometers from Poldhu. On December 20th, 1902, Mr. Marconi sent the first radiograms across the Atlantic to the Kings of England and Italy. Shortly afterward, another station was erected at Cape Cod in Massachusetts, the distance to the Poldhu station being 3,200 miles, or 660 miles further than the Glace Bay station. On January 16, 1903, a complete radiogram was sent by President Roosevelt to the King of England. Professor Fessenden commenced in 1897 the development of the system which is now the property of the National Electric Signaling Company. For 2 years he was engaged by the United States government for special research in the subject, and had the advantages of all the resources of a government department at his command. His inventions are very numerous, and in many respects original, and his results show a precision and a practicality not attained by many other experimenters in the same field. Magnetic, thermal, and electrolytic detectors, methods of exact tuning, and even wireless telephony are covered by Fessenden's patents. Among these, perhaps that which has contributed most to the success of the system is the barretter. In its original form, this was a thermal receiver depending for its action on the change of resistance in a very fine platinum wire when carrying the jig current. Latterly, the continuous wire has been discarded in favor of an electrolytic coil, one electrode of which is an extremely fine point. The apparatus has been described more fully under wave detectors. An important feature of this system, which greatly aids secrecy of transmission, is the arrangement of the sending key, which does not break the circuit but merely alters the wavelength of the waves given out by cutting out some inductance. Thus, unless a receiving station is tuned with extreme accuracy to the transmitter, it will receive instead of signals only a long continuous dash. Hence, only a very sharply tuned receiver will receive a message at all. In the latest forms of apparatus, the difference in frequency between the waves sent out during spaces and those sent as signals is only 0.25%. Interception by rivals is therefore almost impossible. Fessenden is apparently the first to use an aerial consisting of a steel tube standing on an insulating foundation and held in position in insulated stays. The following guarantees are made for the Fessenden system by the holding company. Guarantee for distance: 1 kilowatt set, 250 miles. 5 kilowatt sets, 400 miles. 20 kilowatt sets, 700 to 750 miles. Guarantee for the preventer used to prevent other sending stations from interfering with the receipt of messages. Where the distance of the interfering station from the receiving station is more than 1% of the distance between the sending and receiving stations, a difference in wavelength of 3% is sufficient to cut out the interference without the signals being appreciably weakened, interfering and sending stations being of equal power. Guarantee for the secrecy sender. With our latest form of secrecy sender, the variation in wavelength is guaranteed to be only 0.25% between space and dots. We guarantee that no other system can read the messages. Guarantee for wave measurer. We guarantee this device to be capable of detecting difference of wavelength of 0.25% and to be capable of measuring wavelengths at a distance from the sending station. There are also devices whereby atmospheric discharges will not interfere with reception, and a device for modifying the intensity of emitted waves without altering their length. Communicate with nearby stations. A report giving a description of the Fessenden system as applied to transatlantic signaling between Massachusetts and Scotland may be of interest here. The power is developed by a boiler engine alternator equipment having a maximum capacity of 25 kilowatts, 60 cycles current. A transformer steps up to the voltage to about 25,000, thus charging the condensers, which are discharged by a means of a gap adjustable so as to affect the discharge at any desired point of the cycle. The receiver used is the liquid barretter in its latest form. The aerial is formed by a tower extending to a height of 415 feet above the ground level and supporting a sort of umbrella formed of wires at its top. The tower is essentially a steel tube 3 feet in diameter, supported every 100 feet of its height by a set of 4 steel guys, there being thus 16 guys in all. The tower is pivoted at its base on a ball and socket joint and is insulated from the ground for a voltage of 150,000. The guys are insulated from the tower as well as from the ground. Besides, they are divided into 50-foot sections by means of strain insulators. One of the most serious problems to be solved was the construction of these strain insulators, which, while capable of safely transmitting the maximum stress of about 20,000 pounds, also resist an electrical tension of 15,000 volts each. The maximum deflection of the top of the tower in a 90-mile hurricane is computed to be 15.5 inches. A wave chute containing over 100 miles of wire and extending over 6 acres is a very essential feature of the installation. On January 3, 1906, the first signals were received from the American side, and shortly afterward communication was established so that messages were freely exchanged at night. The intensity of the signals received by telephone was at times so great that the messages could easily be read with the diaphragm 3 inches from the ears of the operator. A station 20 miles distant from Brant Rock, using about 30 kilowatts and sending on a wavelength differing not much more than 3% from that of the Scottish station, was cut out while messages were received from Machrihanish. A system differing in many respects from the other systems has been devised by Sir Oliver Lodge and Dr. Muirhead. The rotating steel disc coherer described under wave detectors is used by them. Another feature is the use of 2 capacity areas at both sending and receiving stations, by the adjustment of which they may be brought into tune. This system has been installed in many places with great success, and although it has not yet operated over such distances as the Marconi and Fessenden systems, it compares favorably with them in syntonizing power and has the advantage of using the siphon recorder. The Telefunken system is based on the patents of Professors Slaby and Braun and of Count von Arco. It may be considered as striking a mean between the earlier systems of Marconi and Lodge Muirhead, though of course with many variations and elaborations in detail. A system of wires, similar to those used by Marconi, forms the aerial, and the earth connection is given by a large capacity, as in the Lodge Muirhead apparatus. A coherer and receiving circuit, in many respects similar to the Marconi arrangement, is employed. The DeForest system has had quite an extended commercial application, especially in the United States. It has the advantage of very rapid signaling, 25 to 30 words per minute having been reached. Communication by this system has been established between Manhattan Beach, New York, and Colon, Panama, a distance of 2,170 miles. The extension of wireless telegraphy and the study of the relations of electrical discharges in radioactive bodies bids fair to be the most fruitful of the fields of the immediate future. The age has been well called the age of electricity, and much amazement ever is expressed that man should utilize so well a force concerning which he knows so little. The complete understanding of the phenomena of atomic force and of radioactivity may go far to unlock many of the closed doors of nature, and the electrical scientist of today is steadily approaching that understanding. End of section 32, and end of the Science History of the Universe, Volume 3, Physics and Electricity, by Francis Rolt Wheeler.